first three questions asks about a pair of points, the coordinates for a pair of points, and asking you if it satisfies each of these equations. So to do that, you take the x value 4 and you plug it in where you see x here, and you plug in the y value -1, and you say, does 4 take away 2 equal 2? And you say, yep. So it satisfies that equation, which means that point, the values, the coordinates of that point is a solution to this equation. So the first one is true. Someone else want to tell me if you had any luck with the same coordinates? Does it also satisfy this equation? Yes, okay, good. So what that means is we call the point for -1 a common solution, because both of these lines, both of these equations has that as a solution. So it's a common solution to this linear system. Anytime you consider a linear equation and you look at more than one linear equation at a time, it's called a system of equations, a system of linear equations, okay? So we're looking at these two equations at the same time, and there's a little typo in here. This should say x minus 2y, okay? So the question is, does this point satisfy this linear system? And we say yes, because we know that for -1 makes the first equation true, and it makes the second equation true. So it does satisfy all three of these, whether we look at each equation individually or we look at the system. All right, so now it says graph each of these lines. Okay, let me just put in a little piece of paper for a minute. A linear equation comes in three forms. Yep. Okay, so x minus 2y equals 6. So x is 4. And where I see y, I put a -1. We're looking at this equation here, Molly? Yeah, it's down there. Oh, yes, thank you. Oh, yeah, there's right. Oh, sorry, folks. Wow, we really messed that up, didn't we? All right. Thank you. All right. So if you said false there, it would have been true. Yeah, equations can come in. Okay. So the linear equations come in a couple of different forms or disguises. The one you're all used to seeing is y equals mx plus b. You know, that's kind of memorized by everybody. This is solved for y. This is called the slope-intercept. I'm not going to get into this. Another form of a line looks like this, which you're probably less familiar with, point slope. The general form looks like this. Okay, and this is the form that I have the two equations you're looking at to graph right now, right? Because one of them is what? X, is it x plus 2y equals 2? Is that one of them? So in this case, A is 1, B is 2, and C is 2. So it's in a general form. And the other equation looks like what? X take away 2y is 6, is that right? And that's in the general form. So the general form, notice, has both your x and y terms on one side and the constant c on the other. So many of you had a little bit of a brain stoppage when I asked you to graph these. I watched some of you. And the reason that you had a little bit of a brain stoppage is because you're used to graphing equations that look like this, where you plug in an x and out pops a y, right? You can still do the same thing here. However, I gave you a little hint. When you have equations in the general form, the easiest way to graph them is with your intercept method, where you find your x-intercept and your y-intercept. Look at how easy it is when you use that. When you take this first line and you try to find each of your intercepts, let's do your x-intercept. It's set up perfectly for this in your y-intercept. So we know with our x-intercept, our y value is 0. And we know with our y-intercept, our x value is 0. So to find your x-intercept, you put 0 in for y. That disappears, and you get x is 2. Voila, you have 1 point that you can graph, 2, 0. So you come over here to your graph, 2, 0. Okay, perfect. And your second point is your y-intercept. All right, so let's do our y-intercept now. Let's take away that. Our y-intercept is when x is 0, so x disappears, and you get 2y equals 2. So 0, 1. Voila, you have point number 2. 0, 1. And all you need, if you did it correctly, is 2 lines to connect them. So you just put a line in between those 2 points. Voila, there's your first graph. Okay. And if I did it exactly right, I'd have that going there and that going there. It's a little hard with this thing, but you get my drift, right? Okay, I will. Okay, so that's your first line. So you should always label your line. So this is the line x plus 2y equals 2. All right. Then we have the second line, x minus 2y equals 6. Again, that's in your general form. The easiest way to graph it is find your x-intercept and your y-intercept, just like we did a minute ago. So my x-intercept is when y is 0. So when I put a 0 in for y, this whole term goes away to nothing, and x is 6. Cool. My y-intercept is when x is 0. So my whole x term disappears out of my equation, and I get negative 2y equals 6. And when I divide both sides by negative 2, I get negative 3. So there are the 2 points that I need to graph my second line, 6, 0, and 0, negative 3. So I go over here to my graph, and with a different color, I put 0, negative 3, and 6, 0. And then I draw that line in. And you have your studio bookmarks to do this as well, right? So here we go through here. I'm not very good with this thing, but it will get there. Scoot that this way. There we go. And actually, they're supposed to intersect at 4, negative 1 if I did this exactly correct. There we go. All right. So that common solution, now what was the equation for this line? X minus 2y equals 6. The common solution visually becomes the intersection point, 4, negative 1. Because this point is on my first line, x plus 2y equals 2, and it's also on my second line, x minus 2y equals 6. Okay? Well, I don't know what kind of word I want to use to describe it generally, because there are 2 other situations we could be looking at, Nick. We could be looking at a situation where we had 2 lines that are parallel. So what kind of solution set would that have? There wouldn't have any. It would be empty, an empty solution set. And the other situation, which is kind of a little bit of a disguise, you have the equation for one line. Let's say it looks like this. And the other equation looks really different, but it's really just some multiple of it, and it's exactly the same line. And so that has an infinite number of solutions. Okay, so you can have, with any system of linear equations, you could have one of these 3 pictures. Okay, yep, 0, 1, or infinite. For our purposes today and what we're going to be doing, we're going to be looking at this first one, where we're looking at a common point that they both have. And that point is a solution to both equations, and it visually is the intersection point. Okay? Yeah, sure, Kenneth.
I was wondering if you were to take on those 2 equations,
Yeah.
Bring the 2 to x minus 2 equals minus 2y.
Yep.
Then you'd have it in the other.
Yep. 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 All I'm saying is you could put these equations in any one of these forms. Like you could solve this equation for, like you just said, x equals 2 minus 2y, and you could graph it that way. You could solve it for y and call this 2y equals 2 minus x, and then divide everything by 2 and plug numbers in. But it's a pain, because then you got fractions. You'd have negative 1/2 for your slope, and yucky, all right? So all I'm saying is, Ken, in this form, the easiest way to get a quick graph is just to plug in your intercepts, find your intercepts. But you can go back and put it in this form if you want and plot it point by point until you get a good looking line. It's okay to do it that way too. Yeah, I was just trying to show you a little shortcut. All right. Any other questions before I move on today? Anything? All right, so let's take a look at today's teaching demo. We're going to be looking at a system of linear equations in two variables, and we're going to start off with a problem that's from your book. Let's see. Tyler, you want to start us off by reading this? You can say no if you want, or pass. You almost look like Eli Manning when his brother won the Super Bowl. Did anybody catch that up in the booth? Oh my God, the look on his face, it was like, huh? I know, and he's always been the little, like, underappreciated brother, right? Anyway, sorry for the digression on my class video. Okay, Tyler? Okay. So the graph below, this graph has two lines. So you expect to see two different equations, which we see right here. So this graph can be represented algebraically by this linear system. Notice we use this just one little curly Q here. It's just to try to have you see those together as a system. You could have three variables, but if you had three variables, how many equations do you think you'd need to solve that? No? Right. So however many variables you have, you need to have that many equations if you hope to solve it. Okay. So linear algebra is another quick little thing. If you've ever seen matrices, another little way you can solve these, but that's a different class. All right. So this equation, and you got to be careful because many of you are used to just looking at these linear equations, and whenever you see the number in front of x being negative, you think it has a negative slope. But remember, this is not in the form of y equals some number times x plus b. So you got to be a little careful. So it says this equation, negative 3x plus 10y, models the percentage of never married U.S. adults. So that's this blue line right here. And you see the equation for that line is always present in the graph. So you know what the equation is and what the line that represents that equation is. So this line represents the percentage of never married American adults, and your x-axis is the number of years after 1970. So you can see that this percentage is increasing. Okay, similarly, the equation x plus 2y equals 142 represents married American adults in the population, the percentage of married American adults, and that's decreasing over time. Okay, so the question is, what does that intersection point, first of all, what would be the coordinates of that intersection point, and how would we state what that means in terms of the context of this story? Okay, so someone want to just look at what you have on your paper and just give me a quick estimate. We're not going to be exact because, what do you think? 67 and 35. So we'll go with that. 67, 35. Does that seem reasonable to everybody that's looking at their paper? Reasonable? Okay, so we agree it's a reasonable estimate. Okay, so that means we can move on. Nobody's gonna like have a heart attack if we use these coordinates. All right, so you've had a little practice with this with your project that you handed in today when you want to discuss what the coordinates of what they represent in terms of the context. So I'm reminding you here, what does the intersection point tell us? Be sure to describe both variables, x and y, and use the appropriate numbers and the units. So one way you can help yourself is when you rewrite the coordinates, you can put right after the number the units. Like 67 represents 67 years after 1970. And 35 represents the percentage of American adults. So once you fill that in, you can easily make up your story or your interpretation by reading straight across. When you read that straight across, you'll get a literal, explicit interpretation. You can say 67 years after 1970, 35% of American adults, well, what do I say now? If I try to do it exactly that way, do I say 35% of American adults are never married? Why not? Why can't I say, oh, so 37% of American adults are both never married or married, right? So that sounds awkward if I say it that way, right? So I might just be a little bit of an English editor here, right? An English teacher might want to edit that sentence and make it a little like easier to read. So 67 years after 1970 could be stated a little clearer. I could just say 2039, right? So it's the same thing. So in 2039, the percentage of American adults that are both, see, we've got a both here, that are both married and never married is 38%. Right? I was just going to say that. I was just going to say, do we know this to be true? It's impossible because these are models. We're not even in 2039. So it's better to say, instead of are both married and never married, we could say are predicted or estimated to be, whatever.
We get 38, yes. 35.
Oh, I'm sorry. No, I'm sorry. It is 35. You know what? Believe it or not, I still have the number in my head from my first class. They predicted 38%. So I'm sorry. Right. Right. Are predicted to be. So down here, predicted to be 35%, not is 35%. We have no idea what that percentage will be. But if the trend, and this is what we use, we say if the trend continues in the same direction for both of these populations, that's our best estimate or prediction right now in 2016. So nobody in my first class mentioned that. So I'm very happy to hear that Molly made that statement. Okay, so here's the problem, folks. If you're just looking for an estimate and you have a visual graph, you just estimate the coordinates of that point. But often we'll want the exact values of each of those variables, and that's where algebra comes in. And frankly, it's a pain in the butt to draw those graphs all the time. So there are two algebraic methods to solve a linear system, okay, with two variables. One's called addition. Some of you may know this method as elimination. That's another word that's used for it. Your book calls it addition. And the other is called the substitution method. So let's take a look at these two equations. And let's take a look at how we would use each of these methods to solve for x and y. Okay. Now, I know this is a review for just about everybody because you wouldn't have gotten to Math 107 without having seen something like this in an intermediate algebra class or in our courses 096. So the first idea says, can I take one of these variables? I look at one equation at a time. Can I take one of the variables and represent it in terms of the other? In other words, could I solve this equation for x or solve that equation for y? I can look at either one of these, any one of these equations. And this is often the method you use when one of your variables has 1 for the coefficient, like this first equation has 1x in it, because it's a real simple thing to do. You just rewrite this equation. You're going to take this equation. You're going to solve it for x. This is the language we use. Solve it for x in terms of y. So what that means is you have x on one side and some y, a term with y on the other, and some constants and maybe a coefficient. So that's the language we use. Solve for x in terms of y. So to do that, I have to subtract 2y away from both sides. So that leaves me x on the left side and 142 minus 2y on the right side. Now you can either write it like that or you can write it like this. It doesn't matter which way you represent that right side. Okay. So now that you have x in terms of y, you literally get to substitute this right-hand expression down in this pink equation, the second equation, wherever you see x. So where I see x, I'm literally going to take this and plop it right in there for x. So now I have -3, and where I see x, I'm going to put 142 minus 2y. That's called substitute. You can substitute for equal expressions for each other. And then everything else remains the same. It stays in pink or red. I don't know how you see this color. It used to be red, but it's kind of looking pink to me now. What's it look like to you? Pink? Yeah, pink. Rose? Okay. All right. Now do you see why we can solve this equation? Because it's one equation. How many unknowns do you see across there? Right here, we're looking at this equation. How many unknown variables do you see? Just one, y, right? So now we can solve this using our usual methods. You'd use the distributive property here. -426 plus 6y plus 10y equals 160. So let's come up here. So -426 plus 16y equals 160. And we add 426 to both sides. And we get 16y equals 586. And y equals 3.625. No, 36 point. Hang on, I know I caught my error. I found my place value was off. Huh? 36.625, right? Those of you who have calculators out there, is that correct? Okay. All right. But have we found our answer to this system? Do I circle that? Why not? Right. Remember, your answer is a point, and you need two coordinates. You need an x value and a y value. So I know my y value is 36.625. To find my x, I go back to an original equation, not one that I've messed around with. Because if I made a mistake somehow in writing x in terms of y, and I put this value in, I'm just going to perpetuate my error. So I go back to one of my original equations. So I'll go back to x plus 2y. And let's see, y here is 36.625. And I solve that equation to find my x value. So let's see. What's 2 times 36.625? 73 what? 0.25 equals 142. So x equals 68.75. So my common solution is 68.75. So that means in the year 2030, 3/4 of the way through the year 2038, both the married and unmarried population is predicted to be 36.625% with our model that we have. Okay. Any questions on finding that answer? All right. So that's the substitution method. The addition or elimination method involves this idea. So over on the side of the paper, here's page 31 down here. So if I did this, 31 plus 4 equals 35. And 30 plus 5 equals 35. And if I decided I'm going to add vertically both sides of these two equations, I would get 31 plus 30 is 61, plus 9, that's 70. And on this side, I get 70. You see? So I can add, these two equations are equal, and I can add the left sides and the right sides, and I still remain equal. That's the idea behind the addition method. I can add this side of my system and this side of my system, and I still come up with an equation. However, this old name here, or the name that I learned, I want to do that in a way that will eliminate one of those variables. So I come up with one equation with one variable. So to do that, the idea is, I'm not going to teach us as if we were seeing it for the first time, but the idea is to make the coefficient, which is the number multiplying x or the number multiplying y, the two numbers, be opposite of each other. So notice I have a negative 3x here. So if I can have this say 3x, when I add 3x and negative 3x, voila, it goes away. So to do that, I have to multiply everything on both sides of this top equation by 3. Now, what does my new system look like? It looks like this. 3x plus 6y equals 426. So that's my first equation. It's equivalent to my original pink equation because I tripled everything. So that kept it the same. And my original second equation has had no plastic surgery done, so it looks just like it did. There we go. Now I'm going to add everything on my left side together. Voila, this goes to 0. And now I get 16y. And my right side is 586. And now when I divide both sides by 16, I get what? 36.625. Oh, good, great. It's the same thing. It better be. I used these both of these methods are supposed to come out with the same answer. And then you would go back and plug this into an original equation, and you would get 68 for x as well. Your estimation was fairly good. Yep. Okay. So what's the moral of the story? When do you use what? Well, both methods always work. When do I use substitution? I would use substitution personally anytime I'm looking at a system like this and I see one of my variables have a 1 in front. If it has a coefficient of 1, I just take that equation and solve it for that variable in terms of the other. And then I plug it in. If none of them have 1, if they all have numbers, then I look to see, is there a variable that has coefficients that are opposite in sign, at least, so I only have to multiply one of them. Like this one, if I was eliminating y, what could I have multiplied the top through by? What number? No, 5 would have made that 10, and that wouldn't have gotten rid of it. -5, right. So if I multiplied through by -5, then that variable would have gone kaput, right? And then I would have been solving this in terms of x instead of y. All right. So that's the two methods, and pretty much you're going to be using for the story opportunities. I don't call them word problems. For the story opportunities, you're going to be using substitution quite a bit. So you'll have lots of practice with it. So this, okay, why don't you open that up, Di? So, no, go ahead. So there's some very sort of structured ways of coming up with those equations. One of those structured ways that a lot of students find helpful is this table here. Notice the headings of each of these columns and the headings of the rows talk about the story you're telling. So let's read the story and let's put the information into this table. Okay? So who do I get to ask today to read the story? How about Ellie? Does anybody get like bad memories when they see stuff like this, or are they pretty good? Or yes. Which one are they, Jasper?
I have accounting, so definitely like bad.
Bad? Oh, okay. Anybody have like good memories with this kind of stuff? Nobody? No? Okay. Well, as Julia knows, I was in art class yesterday, and it's a bad memory for me. I was pathetic. I couldn't even like show the class anything. She's a star, by the way. So she's going to tutor me in math, in art. So we'll see. Anyway, so look, there are ways to approach these things. If your strategies from the past haven't served you well, can I ask you to be open to considering new strategies? Okay, good. All right. One of those new strategies is define your variables. Whatever you don't know in the problem, you need to assign a variable to it. And you need to use language so you know what the heck those abstractions mean when you put the equation together. So part of this table is helping you define those ideas. So the first thing, and I used to have, when I taught this like in 09-6, I used to have piles of cash here, like a big pile of cash and a little pile of cash. Because we got 2 piles of cash here. I wish we had $10,000 to invest, right? One of them we want to be bigger than the other because we don't want to risk it all in a high risk fund. We don't want to put it all in a low risk. We want to kind of, we're not making them equal, so we don't expect the 2 amounts to be equal. One pile of cash is going to be higher than the other. So any way you visualize it, okay? Or if you're a word person, write it out in words. But imagine 2 hunks, even those like, what would they do? Put it in $100 bills, what, up to 1,000, or maybe they'd have a $10,000 stack. I don't know. I've never got that much cash at one time. A check. Yeah, you're right. All right. So visualize it. You're adding 2 amounts of money together. That's the first thing you're doing. Do you know anything about those 2 amounts of money? You don't. What do you know? Huh? I have $10,000, right? If I added the 2 amounts of money together, I'd have $10,000. Read the question it asks you. How much should we invest in each fund? That's often the key. So the first thing when you're writing this out for me on test 1 is and now because we're in this section versus class 5 section, we get to use 2 variables. We don't have to do one in terms of the other. So we can say X isn't the money. X is a variable, it's a number. So when you describe it, you have to describe it with a quantitative word. So X is the amount of money I invest. Let's say in the low risk fund, okay? I could have said the high risk fund. I'm just picking the low risk fund. It's just the amount of money, that's it. So up here, I put an X. See in that cell that intersects the lower rate with the amount of money in dollars? So it's the amount of money, and I always put my units in dollars that I invest. Y will be, someone want to help me? Quantitative term? Amount of money. And I know you think I'm being picky, but there's really some madness behind this method. Yeah. Definitely madness. Okay, high risk fund. All right, in dollars, right. So that I could put right there. So that's not too scary, right? X and Y. Guess what? You know something about the total of those 2 amounts. It's $10,000. So look, if you go right down the column and put a plus side, voila, you have equation number 1. That's not too bad. There you go. Half of your system is created, right? You've got one of the equations already. The next equation deals with not the total amount of money, but the total amount of what? It's not the total percentage, no. What do we call this thing that we're finding here, this in the next part of the, all right, some of you said you're in business, right? So when we invest money in these funds, what do we get at the end of the year? Interest, right? Right. Well, when we're just assuming 1 year and we're doing this annually, right? So we get some interest. Our money makes money. That's our system, right? So how much money, what's the total amount of money we get at the end of the year on this $10,000? 550, right? That's the amount of interest income. So that's the amount of interest income I earn, okay? Now, how do I represent the amount of interest on X dollars? Well, there's a rate, and it's 4%, which is, we represent the percentage with a decimal. Remember, a percentage has no units on it, no units. And 8% is like this. So if I want to represent the actual amount of income I get at 4%, I have to know how much money I've invested. which is right here, X. And when I multiply those two things, I get my amount of interest on X dollars. So most of you will never do this, but this is what I really encourage. If you can write out these next two sentences, you're on your way to becoming a math teacher. No, I'm only kidding. It really helps you like solidify what's going on here. 0.04x does not represent the rate. That's what a lot of students say, the rate of the money. What does 0.04 times x mean? Wait a minute, one person at a time. Just raise your hand so I know who's talking at me. Yep. Percent interest increase. 0.08y represents the amount of, this is where you can use your little ditto things, earned on y dollars. Well, if you set up this table, the heading is going to take care of that for you. The amount of interest earned on X dollars and the amount of interest earned on Y dollars. And voila, when you add those two numbers together, you get your 550. 0.04x plus 0.08y equals 550. And there's your system to solve. And you use one of the methods we just learned a few minutes ago to solve that system. Okay, so what I'm going to do to just save some time is while you start working on your class activity, I'm going to solve this system for you without the video, without recording anything, and you can go back and look at it. Anybody can, I'm sure you can solve this on your own, but I'll do it for you. And you can start class activity, and then like in 10 minutes, I'm going to stop you and have you work on class 5, okay?